Alright, here's a scientific notation review from our notes from last week. Remember last week we talked about the three components of scientific notation: your coefficient, your base, and your exponent. And so those are the three pieces that you remember. Last week we talked about the rules for each. The coefficient is greater than or equal to 1 and less than 10. Your base is always 10. Remember, that's multiples of 10. And then our exponent can be positive or negative. And this indicates the size of our number. Positive exponents are large, and negative exponents are small numbers, smaller than 1. We can put that there. So small numbers less than 1. And in our notes, we went through a couple examples converting from standard notation to scientific notation. And so we talked about getting our coefficient, meeting our coefficient rules. So we went and we found that 4.32 would meet the coefficient rule greater than or equal to 1 and less than 10. And then we counted the number of times our decimal place had to move, and we looked at our positive 7 exponent, so 4.32 times 10 to the 7th. And then we looked at a very straightforward and easy rule, looking at our coefficient and comparing it to the standard number. So in this case, our coefficient is 4.32, and we compare it to the standard number, and we see that the coefficient is smaller. And so since the coefficient is smaller than the standard number, we had a positive exponent. And that rule always rings true when we measure or compare our coefficient to the standard number. Then our second example was looking at a number smaller than 1, so this decimal place. We found that our coefficient rule featured 3, 4, and 2, and we shifted that to 3.42. We then looked at our decimal place and saw that it moved 1, 2, 3, 4, 5, 6 spots to make that coefficient, and we then compare our coefficient to our standard number, and the rule is if the coefficient is larger than the standard number, then we get a negative exponent. So in this case, 3.42 is larger than 0.0000342. So we know that converting has to be a negative exponent. So that's how we get 3.42 times 10 to the negative 6th. Alright, and so now we get converting from numbers in scientific notation to standard notation, and then really just working backward. And so let's look at our rule. If we have a positive exponent here, we know that the coefficient is going to be smaller than our standard number. So if we start with the coefficient 6.3, we have to move our decimal place 9, or the point 9 places, and in order to make the coefficient smaller than the standard numbers, our decimal place would have to move to the right here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's our new decimal spot, and then we have to put our zeros in to make our number. And so our number here is 6, 3, 0, 0, 0, 0, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and another 0 to make sure. And then we just put our commas and we get 6.3 billion. So that's that number. So again, our rule, if positive exponent, positive 9, the coefficient is smaller. And then we can look at converting a number with a negative exponent. And so again, our rule, these should be pretty familiar at this point. We look at a negative exponent, we know the coefficient is going to be larger than our standard number. So in this case, the coefficient is 5.97. We have a negative exponent, and so we have to convert to a standard. So we start 5.97. We know our standard number is going to be smaller, the coefficient is larger than the standard number, so in order to do that, we would have to move this to 3, 4, 5, 6, 7. That's our new decimal place, and then we put in our zeros. So we'll have 6 zeros, and then we can write that new number 0.00000597. All right. So those are your rules for converting to scientific notation from standard numbers and then from scientific notation to standard numbers. Let's look at some examples. All right, so here we go. We have some practice questions here. We can talk about each of them. So let's do the converting from standard numbers to scientific notation. So if we talk through the first one, we know our coefficient looking at this has to be 2.39, and then our decimal place is there at this point, and then we can count backwards 1, 2, 3, 4, 5, 6, 7, 8, and times 10 to the 8th. That's going to be positive because our coefficient is smaller than the standard number there. 0.54 or 0.54, we're going to have 5.4 as the coefficient times 10, and then our coefficient compared, we'll compare the two. Coefficient is larger than the standard number, so that's going to be a negative 2 there. And now our next example, 6,940. Our coefficient is going to be 6.94. And then we move our decimal place 10 to the 3 because our coefficient is smaller than the standard number. There we go. All right, opposite here, going from scientific notation to standard, we look at our coefficient, positive exponent, we're going to have a larger number. We have to move our decimal place 4, so we're going to have 22,000, and that's a comma right there. Negative exponent, that means our number is going to be smaller than the coefficient. So we start off at 409, and then we're going to have 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, 0, 0, 0, 0, 0, 0, 490. It's a little cramped there. Sorry about that. 6.12 times 10 to the negative 2. Coefficient is going to be larger than the standard number because we have a negative exponent. Move it 2 to the left here, so we get 0, 6, 1, 2 with our decimal place right there, 0.0612. And then 3.81 times 10 to the 7th. 7 is a positive, so that means our standard number is larger than our coefficient, 3.81. 1, and we need to go 1, 2, 3, 4, 5, 6, 7. And we put 1, 2, 3, 4, 5. There we go. So we have some big numbers there. 381 million. Just make sure. Good. 38,110,000. All right, I hope that helps.